Okay, so to start this video, we will first start with describing how smell and taste work. So we'll go up here. We will start with taste. So basically with taste, what happens is that we have, so this is the tongue right here. If this is the tongue, then on the tongue, we have various kind of indentations, you could say. And anyway, in each of these, we have these things called taste buds. And taste buds contain a bunch of different cells. On average, I believe it's 125 cells. And yeah, so those are taste buds. And in each taste bud, we have, or in each cell, we have different cells for different flavors or different things that we eat. So we have salty, we have sour, we have sweet, we have bitter, and umami, which is like Japanese or something for delicious or something. Okay, so then we'll start with salty. And these are called papillae. So these things that kind of house these little indentations that house the things, and there's different kinds of papillae, but we'll just focus on the taste buds right now. Okay, sorry. So salty. First, what we need to do is, so let's say we eat a food, it gets dissolved on with our saliva, and those dissolved particles come in and hit these cells and cause certain responses. So what activates the salty sensation is sodium, which kind of makes sense because salt involves sodium. Anyway, and so sodium comes in through just a leak channel, and it depolarizes the cell. So that means anytime there's depolarization, most of the time we're going to have a voltage-gated calcium cell or a channel, and that is going to come bind to these vesicles, bind to the snare proteins and cause the release of a neurotransmitter, which then gets sent through the neuron, and gets sent to the brain, and that's how we interpret salty. With sour, it's the same thing, but this time the activator for sour is hydrogen. So again, it comes through. This time we have voltage-gated calcium and potassium channels that come in. The calcium binds to the snare proteins, releases neurotransmitter, and same thing, goes to the brain. Bitter, sweet, and umami are all the same, and they use, so their main players are ketones and calcium. So with all of bitter, sweet, and umami, basically what happens is that ketones come and bind to a G protein, coupled receptor. And this G protein, once we have that activated, it'll activate this phospholipase C, which then produces IP3. IP3 then comes and acts as a ligand to open a channel in the endoplasmic reticulum and release calcium, which then binds to the snare proteins and then releases this neurotransmitter into the synapse, causing depolarization. And I think that's it for taste. So, yeah. Oh, and I think with so I guess I didn't mention the main neurotransmitter that is used is, I don't know if we talked too much about it, but I think glutamate is the main one. Anyway, so then we'll move on to smell. So smell goes hand in hand with taste. Smell is kind of what amplifies taste. That's basically what happens. This is how we drew it in class, but I think this is wrong because the textbook showed it a different way, where this olfactory bulb was. It said it was up here, and that this was like an epithelium type thing down here, and that the olfactory epithelium, olfactory bulb was up here, and then you have the bone, this or part of the skull that goes into the brain. Anyways, that's the layers. So epithelium, bone, olfactory bulb. So what happens is that we have the epithelium. So, well, we'll just zoom in here, down here. So this is a neuron. And this neuron is embedded in the epithelium and goes all the way up through the bone, into the brain, into that olfactory, goes to the olfactory bulb, then goes to the brain. Anyway, so what happens is if we look closely on this neuron, we're going to find a G-coupled protein receptor. And just the same thing with we were looking at with bitter, sweet, and umami tasting. Use the G-coupled protein, except in this case, it's going to activate. So some dissolved particle that we smell, it's going to get dissolved, and then it combines here, and then what's going to happen is that it's going to activate adenylate cyclase, which then produces CAMP, cyclic AMP. Cyclic AMP then comes and opens this cation channel. And cation channels, this one isn't selective, which means that it'll just let in and out whatever it wants, or whatever the driving force or gradients want to take them. So in this case, chlorine or chloride is going to go out, and then sodium is going to come in. With chloride going out, sodium coming in, that's going to depolarize the cell, making it very positive, which then sends an action potential, as we know. So once it gets depolarized, it's going to send an action potential, and that's how we interpret what we smell. Let me make sure I got all that. Okay, perfect. So now we'll go to the ear. Okay, so with the ear, sorry, these drawings aren't as neat. I didn't rewrite them yet, but with the ear, so what happens is that when we hear something, sound goes into the ear, the sound gets compressed. So sound gets compressed into these sound waves, or into this canal, at different frequencies. And basically what happens is that the sound waves move 3 bones called the malleus, the incus, and the stapes. So malleus, incus, stapes. These are ossical bones. And then what happens is that these move, so they're very sensitive. So when these sound waves hit them, they're gonna move. Sorry, this is the malleus, incus, stapes. Sorry. This is the eardrum. My bad. Eardrum, malleus, incus, stapes. So what happens is that this is going to move, and it's going to hit right here. This is called the oval window. What happens at the oval window is that, so it's going to hit the oval window, and there's a bunch of fluid in here in the cochlea. So a bunch of fluid in the cochlea, and if we zoom into here, so again, these hit the membrane, that little layer, and then that is going to send a signal all this way, and all that fluid that's inside the cochlea is going to move. And so the cochlea can be divided up into a few different parts. So it's hard to see on a 2D graph, but this top part is called the scala vestibuli, middle part is called the scala media, and the scala tympani is at the bottom. The scala tympani is full of a fluid called pesilymph. The media is called, the fluid in there is called the endolymph, and the fluid in the scala vestibuli is called perilymph. So basically what happens is that this is all kind of the same canal. It just kind of loops back around itself. So it just kind of loops back around, but it's all kind of the same canal. Anyway, so basically the movement of that fluid is going to move this basilar membrane. What happens is with this basilar membrane, if we zoom in even more, so if we took like a cross section and then come over here, we have these different places. So again, scala vestibuli, scala media, and the scala tympani. So the scala media is full of calcium or potassium. So it's very high concentration of potassium. We'll see why in a second. And same with these little hair cells. So these hair cells are also full of potassium because they have little, in this pink here, they have little sodium potassium pumps that pump calcium into these hair cells. The scala media has so much potassium because if we zoom in there, so if we take this little part up here in the top right corner, this little layer, it's called the stria vascularis. So if we take that little layer, come down here. So again, this is the stria. And on each side, we have different channels. And what happens is that those channels, with these sodium channels, potassium is going to leak out and cause this to become full of potassium. So where the potassium is leaking, it's going to be really full of that, whatever space that is. In this case, it's the endolymph and the scala media. It's going to be full of potassium. And that is important because they both places where we have potassium, they're going to have a high desire or driving force to come down here into the scala tympani. And anyway, so what happens, zooming in a little more, so if we go on to this hair cell, so what happens is that when that basilar membrane is when it moves because of the fluid moving in the cochlea, it's going to trigger these little hair cells. So these hair cells have these little hair follicles, you could say, and when it vibrates, it's going to move the hair cells, and it's mechanically attached to potassium channels. And so potassium is going to rush out of the cell because these are now open when these bend. So that'll bend, and all open these potassium-gated channels, which then let a bunch of potassium out of the cell, not out of the cell, my bad. It's going to come into the cell. Yes. So potassium is going to enter the cell because it has to depolarize if we want to hear anything. It's got to depolarize. So, sorry, misspoke. Potassium is going to enter the cell, depolarize this whole thing, which then means that depolarization is going to trigger a voltage-gated calcium channel, bind to the SNARE proteins, and release a neurotransmitter onto this neuron, and that is going to be how we hear. So that's the physiology of hearing. I guess a little bit more on the, I know I asked about it later, so let's cross this out first. Okay. Let's see, we'll skip down here to describe the mechanisms of the hearing, include the part of the middle ear and inner ear and the roles. Discuss how the hair... Okay. So... yeah. So, again, sound comes in, gets turned, or it's compressed into these waves, causes the vibration of these things, which then causes another movement of this little membrane, and it causes fluid to move. And that fluid moving, it'll send these little waves all in the cochlea, which vibrates this basilar membrane. And in that membrane, so this is that basilar membrane, in that membrane are embedded a bunch of hair cells that bend with that movement of the basilar membrane, causing potassium to come in, bind to these, release a neurotransmitter. So as far as we went over the function of everything. Basilar membrane, as far as structure, this is what it looks like kind of unrolled. So, and that it's like that. It's kind of like a xylophone. Because like the smaller ones are for higher pitch sounds or higher frequency, or higher hertz, I guess. And this is for lower frequency. So this is the outer ear. This is the middle and inner ear. So cochlea is inner ear. These are middle. This is outer. And let's see. I think that's about it. Let me double check. Hearing. Okay. Yeah, I think that's it. So now we'll move on to vision. So, okay. So the eye focuses light. So if we see an object, so if we see an object out here, light is going to come in to the eye. It's going to hit the lens. And the lens's job is to bend light. And it bends light onto our retina, which is where we end up. And we'll go into the mechanisms behind that later. But it bends light, and it hits the retina in just one spot. And that is how we interpret things that we see. If we're seeing things farther away, it's going to bend light less. Let's see. So as far as structures, so this is the lens. It's attached to the eye with suspensory ligaments. And it's got these ciliary muscles. So looking down here, if we were to look at it straight on, the ciliary muscles surround the whole thing. When they contract, it's going to contract. All those muscles are going to contract. And then, which means that these suspensory ligaments just kind of loosen up a little bit. They get relaxed, which is going to make the eye bigger. So if you look here, muscles contract. So we loosen these, so there's not as much tension, which makes the lens bigger. The lens gets smaller when those muscles relax, which tightens the suspensory ligaments. So again, this is the case when we are doing things like this is when we're seeing things close. So when the lens is fat like this, it bends light a lot more sharp. And again, opposite with this, less sharp. Actually, if we do a lot of close stuff, like reading a bunch, then our lens can actually kind of become a little more stuck like that, which leads to blurriness because the lens gets bigger, or sorry, not the lens, the eye. Or yeah, no, the lens. The lens gets bigger, which then kind of makes the whole eyeball longer. And that happens, the light has further distance to travel, and so it continues to cross over, and we end up seeing two spots instead of one, which makes things blurry. Concave bends light in, convex bends light in, concave bends light out. I don't know if I need to talk about that very much, but some more structured things. So behind the lens, there are blood vessels. There are blood vessels, ganglion axons, bipolar cells, photoreceptors, and pigmented epithelium. So basically, the parts we'll focus on mainly, are photoreceptors. So photoreceptors are where, in this pigmented epithelium, where light is received. Photoreceptor, there's two kinds. There's cones and there's rods. So cones see color and rods see black and white. So now going further in it. So look at these three players, 1, 2, 3, and then take it down here. So we got the same thing, 1, 2, 3, same players. So to explain the mechanism behind it, light comes in, it's going to hit this thing called 11-cis-retinol, which is this. If there's enough energy, this is going to change. It's going to break that bond, and it's going to change into a trans. If this happens, this whole thing, this little structure right here, is this GCPR, a G protein coupled receptor. So if that happens, that's going to activate PDE, and PDE is phosphodiesterase, I believe. PDE basically comes and eats cyclic stuff. So there's this cyclic GMP that typically binds to a sodium channel that increases sodium concentration in the cell when cGMP is attached. But if we activate this, it's going to break down cGMP, so that channel is going to shut, which doesn't lead to depolarization and doesn't lead to calcium opening and doesn't lead to neurotransmitter, doesn't lead to glutamate being released. Then we got this mGluR6. mGluR6 is activated by glutamate. And what it does is that it goes and turns this off. So if there's no glutamate out here, this won't be activated and this calcium channel will stay open, depolarizing the cell, causing a Bwong, and then going and binding. And so depolarization, which opens another calcium channel, binds to the snare proteins, releases glutamate. Glutamate travels across this AMPA channel, or this AMPA receptor, and causes another depolarization. So that is how we see light with the photoreceptor, the bipolar cell, and the ganglion axon. If we're in the dark, if we're in the dark, let's say not enough light comes in, so PDE is going to be inactivated, so it's not going to do anything. So this channel is going to stay open, depolarize the cell, cause calcium this channel to open, release glutamate. Glutamate is going to bind to mGluR6, which is going to shut this channel and cause nothing here, which causes no neurotransmitter release, no glutamate out here, and no action potential up here. So that's why, obviously, we don't see in the dark, because there are no action potentials. Our brain isn't interpreting anything. Okay, now moving on. Again, same exact players. Photoreceptor, bipolar cell, and ganglion axon. Same things. We're just going to use the same things. So, if we're looking at, okay, so let's talk about receptor fields. So receptor fields are basically a group of photoreceptors. So they're photoreceptors. And yeah, so these, yeah, it's just a group of photoreceptors. And, well, I think it's just this whole thing, just a bunch of these in one little area. Anyway, so we have the center, and then we have the surround area. So in the center, if light comes and hits the center, again, we just learned that light hits, and light is always going to prevent glutamate from being released. So we also have these surround cells, or sorry, these adjacent little cells things. And if, so again, light hits here, but does not hit here and does not hit here. So glutamate is going to be released here and here, but not in the center here. So when glutamate is released, it's going to come into these surrounding cell, or these little cells right here, which is then going to let potassium in, or sorry, calcium, or oh my goodness, sodium, which then releases GABA, which then further inhibits glutamate release. So that works together, and again, just like we talked about, prevents further glutamate release and does that. In this case, it's the exact opposite. So there's not going to be as much glutamate release in these cells, and then just vice versa, what we just talked about. So with this, let's draw some. So if we have a center and outside, let's say light is hitting, let's say light is just hitting this much. So in a receptor cell, the center accounts for 60% of action potentials, and the surrounds account for 40%. So 2 on this side, 2 on this side. So let's say light, let's say this is an on center. Let's say we're looking at this. Or no, yeah. Let's say actually we're doing off center on surround. So these are on and this is off. So we'll color that in to signify that it's off. So it's not getting light, but these are getting light. Or I guess they're on, in a sense. Anyway, so let's say light comes and hits this much, like I just drew. So basically the rule is, if light hits an on center, then we're going to count those action potentials. So we're going to count those. If it's an off center and dark is hitting it, then we count those. So in that case, and then if it's dark and light is hitting it, then we do not count those. Or if it's light, like in this case, it's this light, but light is not hitting it, then we do not count those. Okay, so we kind of only count what the thing actually is. So the middle is dark and it's receiving dark. This outside is light and it's receiving light, so we count those. This outside is light, but we do not count those because it's not getting any light. Anyway, so that's how many action potentials are going to be generated. It's just 6 plus 2. Again, the numbers might vary, but these are percentages. So we'll have 8 action potentials. Let's see if I covered that all. The city buttons. Yep. 2 test photos of those. Okay. Okay, I think that's it.